Okay, right. So what I'm going to do is try to give you a brief overview of the action of a drug once it's within the nervous system, and then talk about a framework for looking at neurobiological approaches to addiction, then talk about some major areas that are involved in drug addiction, and then finally this model, which because I don't work in the area very closely, I don't know whether it's the best model, but it's certainly the one that we teach to our undergraduates, which is a model of addiction by two people called Koob and Le Moal. So there'll be about 4 sections to the lecture, and we'll see how we go. And as I said, if you want to ask a question because you don't understand my English or because I'm too fast, just let me know, okay? Right, so everything starts with dopamine, and this came from a study by 2 psychologists called Olds and Milner. And what they were trying to do is to look at what's happening within the human brain or in the mammalian brain to understand reward. So why is it that we do certain things and not other things? So what they did is that they had this sort of setup here where they had a mouse and or rat, and they had done surgery to place an electrode on certain areas of the brain, and with different animals they put the electrode in different areas of the brain so that they could see the response in different areas. So I'm going to try to play a video to demonstrate what this was. So let's hope this works.
The video clip shows a rat with an electrode implanted in the lateral hypothalamus. The animal can freely move about the cage. By accident, the animal presses the lever. As a result, a weak electrical stimulation is passed through the electrode. The electrical current activates the reward system, which in turn reinforces the rat's behavior. The rat presses the lever continuously at a constant rate, at the expense of other vital behaviors, such as eating and drinking.
So basically, just to summarize again, they had through surgery, they had the electrode placed in different parts of the different rats' brains, and the rat was just moving around. And what they did was that if the rat pressed this lever, so just like a door handle, then they would get a stimulation through this electrode into the particular part of the brain. And what they found is that in the animals where the electrode was in the septal areas of the brain, the rat got very excited and learned that whenever it pressed this lever, it got more of a stimulation. And what you saw there was the rat constantly doing this. And what they said in the video is that the rat would do this even despite the fact that it was hungry, it needed to do other things, etc. So effectively, the rat became addicted to this stimulation in that part of the brain, and it was performing an action, which is pressing this lever to get that stimulation. Whereas in other parts of the brain, when they activated it through the same thing, but in a rat where the stimulation wasn't in the septal areas, you didn't get that same behavior. So does everyone understand that general experiment? So through that, they worked out that there's a certain area of the brain which is important. So they said there are numerous places in the lower centers of the brain where electrical stimulation is rewarding, in the sense that the experimental animal, the rat, will stimulate itself in these places frequently and regularly for long periods of time, if permitted or allowed to do so. And so this is what allowed them to potentially talk about reward centers, because it seemed that activating that area in the brain, the septal area, seemed to be giving some sort of reward that created this behavior that made the rat keep wanting to do it over and over again. Okay?
Yeah.
So, That resulted in a lot of work on brain regions and neuronal pathways. So as you guys know from analgesia, etc., that you have to do, you have the neurons that pass information through the brain or the nervous system. Now, where the brain is concerned, the thalamus, deep in the brain here, it receives information from the rest of the body through the spinal cord, etc. And then it processes this information, and then it sends it to other parts of the brain about what you're feeling in terms of your touch, etc., and if you're feeling any pain. So the thalamus becomes a really important area for our physical perception of the world. So this reward pathway that Olds and Milner had discovered with the rat is activated whenever you see the possibility of positive reinforcement. So we have this information coming in somehow in this reward area here that was discovered with the rats, which is next to the thalamus. And whenever you either receive reinforcement, so the activation, or you see the possibility of positive reinforcement, so the possibility that the chocolate is there, etc., this area becomes very activated. Mm-hmm. So this is the beginnings of our understanding that this section of the brain is very important in reward and is probably involved in what happens through addiction. Is that okay?
Okay.
Okay, so as you know, electrical impulses move down the axon of a nerve cell, and it goes towards the terminal or the end of the particular axon. And the terminal makes some sort of synapse or connection with the dendrites, which are the arms of this nerve cell. So this axon here is attaching to this other nerve cell here. And these two are talking to one another, and it's through the synapse, the connection that they make, that the neurochemical signal is passed from this one here into that one there. So that's the basis of all neurochemical transmission. And so these terminals, they can synapse either onto the dendrite or the soma. It doesn't matter what that's different. So now we come to the important thing, the synapse and synaptic transmission. So as an electrical impulse arrives at the terminal, it triggers these little packets, these little bundles of information, of neurotransmitter. So this little bag contains some chemicals, and in this case, dopamine. So when the nervous impulse has arrived down here, so it's been sent down from the soma of the axon, it comes down here, and then what that does is at the end of the dendrite, it activates this parcel to move to the end to this bit here. So that's what the electrical impulse does. It tells it to get ready to pass its information onto the next nerve cell, because everything here is about transmission of information from this nerve cell to that nerve cell. Mm-hmm. And what happens is that the vesicles, which are these packets of the neurochemicals, they fuse through some neurochemical process to the membrane, so the end of the nerve cell here. And when it fuses there, it basically opens this bag, and it allows the little gray guys that are in there that look like little coffee pots to release those little coffee pots out here, and that is how the dopamine is released. So once outside this synaptic cleft, which is this space in between the two neurons, once inside the synaptic cleft, so this cleft is the space between neuron number 1 and neuron number 2. So it's the little gap there. We have the dopamine, which is now free flowing in here in the space, And that dopamine can bind to specific proteins, which are receptors, which are on the membrane of the next neuron. Now, the thing that differs is that each neuron has got different vesicles and therefore different types of neurotransmitter, but also each neuron has different types of receptors. So not every neuron will have dopamine receptors, and not every neuron will be able to release dopamine. So this is only the example for where dopamine is concerned. So in terms of dopamine neurotransmission, what happens is that neighboring neurons, so neurons nearby, they release compounds called neuromodulators, and they enhance or inhibit the effects of the neurotransmission. So they either help or they make it worse. So here we've got the first neuron, we've got our second neuron that it's trying to send information to, but you've got a neighboring neuron here, a third one. And this third one here has got this neuromodulator called endorphin, and this binds to opiate receptors in this one here, the postsynaptic cell, and therefore it can affect whether the dopamine is passed this way or not. So effectively, this thing here, the endorphin that's being released by the third neuron, is going to either increase the chance of the dopamine being passed on to this neuron or reduce it. So that's why it's a neuromodulator, because it can either help or make it worse. These endorphins are destroyed by enzymes in that synaptic cleft, so they don't last there all the time. But it does mean that if you've got neuromodulators near these two neurons, then they can affect what's happening. So that's quite technical. The details aren't important, but the main things to take away from this are that we have neuron number one, it's got a message to send. We've got neuron number two that it wants to send a message to, and it does it through these little coffee pots, which have got dopamine in them, which are going to then pass the information down here. And sometimes, not always, but sometimes you've got other neurons nearby that can release information through these neuromodulators, which can either make it easier for the information to go past this way or make it worse.
Pietro, grazie.
Ashok, we're asking if it's possible to
Agire.
to act upon the neuromodulator enzyme, so that the enzymes that degrade the neuromodulator.
Right, the endorphin, you mean?
Yeah, well, in this case, endorphin, but any.
Yeah, yes, exactly. So that's what the pharmacology would be. It would be about different drugs that either improve the availability of the endorphin or reduce it depending on what the particular condition is. So yes, so the release of this neuromodulator from the third neuron, that is something that you can alter, and that's what the pharmacology would be about. Right.
So I think is that done through enzyme, like slowing down the enzyme, or just simply by allowing more of the the neuromodulator to be present?
That I don't know, I'm afraid, because that would be about the biochemistry, which I don't know about, I'm afraid. Right. Okay, so now, of course, the reason that I've been talking about dopamine is because dopamine is very involved in that reward pathway that Olds and Milner found with the rat, and which we know is very important in generally any pleasurable activities. So we know it's involved in many different processes, not just addiction, but it's a very important neurotransmitter for anything that involves a happy feeling. So in relation to addiction, dopamine plays a role in many different processes that are relevant. So anhedonia, which is the feeling of feeling unhappy or flat. Things to do with our learning, so the way we make selections and how we learn, how we attend to different information, incentive salience. These things aren't really important for you to know. You just need to know that these are all different processes, and most of them are psychological processes that either improve our behavior or they reduce our behavior. The details of them are not important, but the main thing is that dopamine is really important for a number of different aspects of behavior. And psychologically, this is what they are, but I'm not going to go into those because they're not important to what we're going to be talking about. So just so you know that addiction is a very complex behavior, which involves lots of different things, such as your attention, your the way that you look at certain incentives, such as drugs or alcohol, etc. Whether you become more motivated or less motivated, etc. So dopamine is involved in all of these different aspects, and that is why there is so much work on dopamine and addiction. So looking at reward pathways implicated in addiction. So here again, we've got that central area in the old part of the brain. And so these were the areas that were discovered in the rat by Olds and Milner, where you've got the ventral tegmental area, the VTA, and then the nucleus accumbens. So we've got information coming in from up the brainstem, up the spinal cord to this area. So that's where information first starts being processed. And what we know is that all pleasurable activities, drinking, sex, food, etc., they activate the VTA area. In addition, we know from the work with the rats that electrical stimulation directly into that area also is involved in reward or pleasurable feeling. But we also now know that all of the addictive drugs, such as opiates, cocaine, cannabis, nicotine, and also behavioral addictions, such as possibly shopping, gambling, etc. They're all somehow linked to activation here. So that's really important to know that addiction is built on a neurobiological system that is already there, because we feel pleasure through drink, sex, food. That is a pleasurable thing. And this is the area of the brain where you begin to feel the enjoyment from these activities. And this was discovered, as I said, from the work with the rats, that we know that this area is important. So these drugs, they're not working on a new system. They're working on a system that has already been developed through evolution, which is for pleasure. Does that make sense? So addiction is actually just an extension of pleasurable activities. Okay? So what happens when one of these things, when we do engage in one of these activities or take one of these drugs, etc., is that the VTA is linked to the nucleus accumbens. And the reason that this is important is that the nucleus accumbens is linked to the prefrontal cortex. And the link to the prefrontal cortex is extremely important because of the behavior and the control of behavior that I'm going to be talking about later on. Okay, so this is I think this slide is quite important. So does anyone have any questions at that point?
So Marco was asking if the prefrontal cortex and the nucleus accumbens are reciprocally communicating with each other.
That I don't know. I don't know whether it's a one-way communication or
I think yeah, it should be both ways.
Okay, no, I wouldn't know. Okay, so shall I go on?
Yes.
Okay. And Pietro, funnily enough, while I was giving this lecture in 2014, I realized why everyone was interested in Jeff, because until this point, I didn't understand why the people working in psychopharmacology were interested in Jeff. It was only when I was giving this lecture that I understood it.
Yeah, well.
So now, okay, so now we come to the action of different drugs. So I'm going to look at the action of heroin to begin with. So heroin gets into the brain very rapidly when it's either injected or smoked. And what happens is that enzymes convert heroin into morphine, and which binds to opiate receptors, so like receptors with the dopamine that I was talking about earlier, which are all over the brain. So you see the green dots here, here, this area, that area, etc. So there are opiate receptors everywhere. So they're in parts of the cerebral cortex, the VTA, the nucleus accumbens, the thalamus, and the brainstem. So we've got receptors for morphine everywhere, these opiate receptors. So the result of that is that if you take heroin, because the enzymes can convert it into morphine, you're effectively giving all of these different areas morphine. And in particular, the important thing is that some of those areas are the VTA and the nucleus accumbens, which we know from the other work are involved in the reward pathways. And it's also the pain pathway through the thalamus, the brainstem, etc. So this is what results in analgesia. So this is why heroin is such an important drug, because it results in the pleasurable activities that we know from this work, the reward pathways, and it also is involved in the pain pathways, hence the importance of heroin. So what happens is that morphine binds to opiate receptors on a particular neuron, and it causes it to release a neuromodulator called GABA. And I don't know the details of that, but opiate receptor is there. The morphine, which is the green guys here, it attaches to the receptor there. What GABA normally does is that when GABA is in this area here, it inhibits the release of dopamine from this neuron. So under normal circumstances, without the morphine here, what happens is that the GABA that's here, it reduces the transmission of dopamine from this neuron into the cleft and then allowing that to pass down there. So usually GABA reduces the transmission of dopamine, sorry. But when you have the morphine here, the morphine attaches to this third neuron and it reduces the amount of GABA. And so the net result is that this neuron here can release more morphine, sorry, more dopamine into the synaptic cleft. Then this, the released dopamine can then bind onto the receptors here. So just to summarize, if we didn't have morphine here, we would have the release of the dopamine here into this space here, like this here. It would attach to neuron C, and this neuron C would pass down the information. But usually, if morphine's not around, this one here releases this neuromodulator, GABA, and GABA reduces the transmission. So it does something here that stops or limits the amount of dopamine that is released by neuron B. So the result is that when GABA is allowed to be in this space, you have less firing of neuron C. But what morphine does is that it stops the release of the GABA. And because there isn't the GABA in this space here, then it means that more of this dopamine can be released, and therefore the net result is you've got more firing of neuron C. Did that make sense?
It's very clear.
Bene per tutti? Capito?
Very, very clear.
Yeah.
Okay, good. So the opiates, they're in the nucleus accumbens. So this is particularly important in that nucleus accumbens area. So now looking at the effect of cocaine, there are two forms. There's the powdered form, which is the salt that is snorted. And this is a relatively slow route. It goes from the nose to the heart, to the lungs, back to the heart, and then up to the brain. But the freebase form, which is crack, which can be smoked, that has got a much more rapid route. It goes from the lungs directly up into the brain, whereas the purple one is the one that has to go through the heart, to the lungs, back to the heart, and then pumped up into the brain. So this one is a slower route than this one. This is the fast route. Now, what we know, or what's been found out, is that, excuse me, typically the faster the effect of a drug on the brain, the more addictive it is. So effectively, the time between taking the drug, either by snorting it or by smoking it, and experiencing the reward effects, influences the likelihood of abuse. Now, this comes from very standard information that we know from human and animal learning, that if two actions are very close to one another, then the likelihood of that behavior being reinforced is increased. And everyone knows the famous work by Pavlov with the dogs. If the bell was rung and the food appeared, then the dog starts salivating. But if they increased the gap between the bell being rung and the food appearing, if they had a 5-second gap and then a 10-second gap and a 15-second gap and then a minute, 2 minutes, etc., if they increased the time gap between the bell ringing and the food appearing, then eventually there would be no salivation by the dog and you wouldn't get the classical conditioning. So in the same way here, the faster the drug being taken and its rewarding effects happening in the brain, the more likely the abuse is going to be. So this is why snorting cocaine is different from smoking it, because the smoking gets it into the brain much more quickly, and so that link between the smoking and the hedonic effect is increased.
Okay.
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 Looking at the
Come?
Più rapido è l'effetto e più c'è la probabilità di indurre abuso.
Sì, lo sviluppo
Dipendenza.
Lo sviluppo di
Dipendenza.
okay.
Okay.
Okay, so looking at the location of these cocaine binding sites, cocaine can reach all areas of the brain, but binds to specific sites. And in this case, it's these yellow dots here, which are near the, again, VTA, the nucleus accumbens, which we know are the reward pathways, and the caudate nucleus. And the caudate nucleus is involved in certain types of physical behaviors where you repetitively do things like walking around, biting your nails, scratching, etc. So we can see from where the sites are where the cocaine binds, the types of behavioral problems. We have the reward pathway here, which means that the likelihood of addiction is increased. And then because also the caudate nucleus, which is over here, which is involved in these physical behaviors like walking backwards and forward and scratching and nail biting, why they increase with cocaine as well. So can you see that because of the areas that cocaine binds in the brain, That's why we get the different types of behavioral patterns. We have the addiction, and we also have the physical thing with the moving around, the scratching, etc. Does that make sense?
Yes, clear.
Okay, could I just have 30 seconds? I just need to go and get something. 1 second.
Ragazzi, tutto chiaro?
Chiaro, sì, per ora sì.
Come va?
Bene, molto.
Bene, il mio nucleus accumbens è sovraeccitato.
Cosa hai preso?
Niente, solo vedere questa presentazione.
Bene, bene. Si capisce?
Sì.
Ok.
Okay, ready?
Ready.
Okay, so now looking at the action of cocaine, it binds to those areas, the VTA and the nucleus accumbens, that we know are rich in dopamine synapses. And under normal circumstances, the dopamine inside the terminal is released into the synaptic space, and then it binds here. And then it's taken up again. So after it's been biochemically bound to this receptor and it's information down, the chemical is still left here. And these pumps, they act like a hoover, and they suck up what is left, and they take it back into the first neuron. So that's the normal action. The dopamine is released here, and some of it will bind bind to these receptors here, and then the action gets passed down here. But if there's anything left over here, what happens is that these uptake pumps, they're used for getting rid of anything that's left over. What happens is that when cocaine is in this space here, it actually binds to the uptake pumps. So it attaches to the pumps and it stops them from working. So the result is that the dopamine can't be pushed back in here. And the result is that you end up with more dopamine in the synaptic space, and then eventually. So just to summarize again, usually without the cocaine there, the nervous impulse comes down here, the vesicle comes to the end, and it binds to the membrane here. The little vesicles of the dopamine, they get released. So you have all these little Nespresso pots here with the dopamine, and they then bind to here to pass the information down to the next one. But as part of the normal process of keeping things tidy, the synaptic cleft has a system of cleaning things up, that after a few milliseconds or a few seconds, I don't know what the time is, these little hoovers come around, the yellow ones, which take away a dopamine that hasn't been passed down here. So there's only a limited time that this dopamine can attach to these receptors here to pass the information down, because if they don't do it quickly enough, then they'll be taken back up with these take pumps. What happens with the cocaine is that the cocaine stops these pumps from being active by binding directly to the uptake pumps, and the result is that we don't have this movement of the dopamine back into the first neuron, and so the dopamine can remain in the cleft here for longer, and because it's here for longer, any of these ones that haven't found a receptor yet, they can spend more time looking for a receptor and passing the message down. So what cocaine is doing is reducing the take up back into the first neuron of the dopamine. Does that make sense?
Yes.
Yep.
Okay.
So in both substance, we have a longer time
for dopamine into the synaptic cleft.
Yes, and it's happening in different ways, but the final result is the same.
Okay.
Dopamine being passed into the next neuron for longer.
Mm.
So the action is happening differently here. For one of them, it's to stop the inhibition of dopamine release.
Yes, yes, I see.
The previous one, for this one, it's to stop the sucking up of the dopamine. But the end result is still the same. There is more dopamine available in the cleft, which means that there's more possibility of this neuron here finding a dopamine parcel to send the information down. So the actual action of cocaine and heroin is different because the morphine works through the GABA, whereas the cocaine on these uptake pumps, but the end result is still the same.
Thank you.
Okay. So that's about those two main drugs. Of course, there are other drugs as well, but this is just an example. And you see that with cocaine, it's more in the nucleus accumbens. With morphine or heroin, it will be in a different area. And this is why different drugs will have slightly different profiles. But overall, and now we're moving into the psychology of drug taking. This is a framework of this model that I told you about, the Koob and Le Moal model, which is of, the behavior of addiction. And within this model, we first of all have preoccupation and anticipation. And this is where you're thinking about the drug. So there's a desire for wanting to take the drug, you're thinking about it, etc. And there's a spiral that's happening where you've got various different things going on. But the first thing is that after you start taking the drug a lot, because you've decided, I really like this feeling, you have what's called binge intoxication. So you're taking a lot and now you're intoxicated and you're in some form of addiction. Mm-hmm. Then the next thing is that you start feeling some sort of withdrawal, and that's the negative effects. And just that is more, sorry?
I just wanted to translate what binge means in Italian because it's not.
Oh, sorry, yeah.
They might be familiar with. Binge vuol dire utilizzo frequente, cioè come si usa adesso per esempio per dire con Netflix, no? C'è il binge watching, ovvero guardare tutto immediatamente, no? Cioè, magari
si può definire abbuffata?
Sì, una sorta di abbuffata. Se capite tutti gli altri termini.
Intossicazione da abbuffata. Dice...
E è tipico il binge drinking, cioè quelli che vanno in discoteca e bevono non piano piano, ma cercano di ubriacarsi nel più velocemente possibile.
Esatto, sì.
Aspetta.
Okay. Oh, yes, sorry.
No, that's okay. So what we have are three phases. First of all, this taking a lot of something, so binge on TV or shopping or whatever. And then after a little time, there's this negative withdrawal of the negative side of taking the drug. And then the third thing is a preoccupation, and all you're thinking about is taking things. So I made an error before I started with this. In fact, this is the third one. So first, it's binge intoxication, where you take something and you think, oh, this is very nice, I like it, I will have some more. Okay, let me have another one. Okay, I'll have a third one, a fourth one, etc. So this is the binging. Then when you don't have the drug because the drugs are finished or there's no more alcohol or your internet is dead and you don't have Netflix, that's when you have the withdrawal and the negative effect. And when you have the negative effect, that creates this preoccupation of, I want more, where can I get it, where can I get it? And so you now are in a state where you're thinking about it, and this is when addiction has started. So what I'm going to do is now go through these 3 different phases, but is everyone happy with the fact that it starts first of all with doing a lot of something, and that feels really good. Then the negative effects, and then finally the preoccupation with when can I get some more, and this is where addiction starts. Is that okay?
Yeah.
Looking at binge intoxication, this work has typically focused on the positive effects of the drugs, which go through the dopaminergic pathways, which I've just been talking about. So that's what we've already been talking about, that why is it that initially the drug, the alcohol, etc., makes people want to do more? It's because it feels good, and that's because of the brain reward pathways. So that's how the binge intoxication starts. And it also involves other neurochemicals, so serotonin, opioid peptides, and GABA. But I'm not going to go into those because I don't know about them. But just so you know that dopamine is the big one, but there are these other guys as well that are relevant to addiction. Now, what's been found is that acute drugs of abuse are associated with decreased reward thresholds. And what that basically means is that if you just give small amounts of this, whether it's alcohol or the drug, then eventually the reward threshold gets lower and lower to the point where you're not having any effect whatsoever. But that bit isn't important. The more important bit is the withdrawal and the negative effect. Now, the withdrawal is defined as the chronic irritability, anxiety, depression, anhedonia, so that's feeling flat and nothing good, low motivation for natural rewards, and it's known as the dark side of addiction. Pietro, do you think it's necessary for that to be translated?
Oh, it's very clear.
Perfetto. Gli altri avete capito?
Io ho capito.
Sì, chiaro.
Entra, tutto bene?
Sì, sì, ci siamo.
And this is because of now hypoactivation, so underactivation of the dopaminergic pathways. So this results in increased brain reward threshold. So now what you need is more and more of the drug to get some sort of hit. So here, what's happened in the withdrawal period is that you no longer need just a small amount of alcohol, you need more, and you need more, and you need more. And this is why for someone who's an alcoholic, it's not about having 3 vodkas, it's having a whole bottle of vodka, because their reward threshold has become really high. And something that will make you and I feel quite nice after one small glass of wine, they need a whole bottle of wine or a whole bottle of vodka. And that's because the dopaminergic system has become really underactivated. So they really need a lot of activation of that. And this is where the craving for more and more of the drug comes in. And what happens is that it recruits what are known as anti-reward systems. And these are in other areas of the brain, which involve the amygdala. It involves something called corticotrophin releasing factor, called CRF, dynorphin, which is the opposite of endorphin, norepinephrine, and these are between system adaptations. I'm not going to go into this, but this is about how between different areas of the brain, there's a different equilibrium that is set up. We go into that, just that there's lowering of the dopaminergic system, so then you need increased amounts of the drug, but also these areas of the brain that make you feel negative, they become activated. And these...
Excuse me, what's the dynorphin? I don't know.
It's another neuromodulator. I don't know anything.
Noradrenalina.
No?
No,
No,
no.
norepinephrine is noradrenaline, but dynorphin, I suppose it's related to endorphin, and it's probably the opposite of that. So it's probably a negative form of endorphin.
Ok.
I don't know it myself.
Quindi non è, scusate se intervengo così a cavolo, abbiate pazienza. Quindi la norepinefrina non è la noradrenalina?
Sì.
Sì.
Ah,
La
quello sì.
norepinefrina è noradrenalina.
Ok.
La dinorfina, la dynorphin, non si sa.
Ok. Stiamo andando a cercarla, cosa dice?
Sì, è un opioide.
È un opioide?
Opioide endogeno che calma
Are you
l'ansia.
looking it up?
È un opioide endogeno che calma l'ansia.
Sarà endorfina, tipo
Quindi
endorfina.
agisce, vedete, al contrario della norepinefrina.
La norepinefrina
È un
è
antagonista.
un'endorfina.
È un'endorfina.
Sì.
Ok.
Ok. Comunque c'è questo adattamento tra i sistemi.
Sì. Un equilibrio.
Equilibrio.
Ok.
Ok, Ashok.
Okay, so these different systems, both of these two here, they're in stress responses and are trying to restore balance during the chronic phase of the drug. So not the initial phase when you're enjoying the drug, but later on when you're missing the drug. And they produce negative effects and stress-like feelings during this period. So the first period, the binge intoxication, was the nice stuff from the dopamine. But now when we get into the second phase here, when there's hypoactivation, so lowering of activity of this system, you get all these negative things coming in. Then the next phase, the final one, is the preoccupation and anticipation. And the factors that are involved in this protracted abstinence via negative reinforcement are triggered by this withdrawal effect. And what's happening is that there are changes that are happening in different brain areas that are adapting via the chronic drug use. And the result of that is that these are long-term changes, which is why you can have relapse and rapid re-addiction. So just taking someone and saying, no, you can't have the drug at all is not going to work because their brain chemistry has changed. It doesn't work like a healthy person's brain because there have been adaptational changes because of this long-term abuse of the drug. So this is all to do with the preoccupation and anticipation, because now it's moved away from pleasurable activity to more to do with control of the behavior. And it's triggered by, it's centered in deficits that develop in the prefrontal cortex. So do you remember that I said that the nucleus accumbens and the ventral tegmental area, they're linked to the prefrontal cortex? Well, prefrontal cortex is where we start getting the behavioral problems, because tension, control of memory, inhibition, which is trying to stop certain behaviors, those are all controlled by the front of the brain. So this third phase is to do with changes that are happening not in the dopaminergic pathways in the reward areas, but more about changes in the link between the reward pathways and the prefrontal cortex, which is basically about overall behavioral control. So looking at the key neuroanatomical structures, the first areas that we talked about were the nucleus accumbens and the central nucleus of the amygdala. And these are all in the forebrain, and they're involved in the rewarding or the positive effect of drugs abuse. And they're the ones that drive that binge intoxication at the beginning. And they contain the key neurotransmitters, which are the dopamine and the opioid peptides. And the extended amygdala, that's composed of the central nucleus of the amygdala, the bed nucleus of the stria terminalis, and the transition zone in the medial part of the nucleus. But details, I don't know too much about, but the main thing is that this area, whereas this area is the positive drugs, like the dopamine or the neurotransmitters, this one is involved with the stress hormones, corticotrophin releasing factor, CRF, that controls our hormonal, sympathetic, and behavioral responses to stressors. And it's involved in the anti-reward effects of drug dependence. So you see that the action is moving from these areas here that are the reward areas and involve the feel-good happy hormones or neurotransmitters, to the extended amygdala, which is a bit beyond these areas here. And it's now dealing with anti-stress hormones, anti-reward hormones. And this is where the dependency is going to happen. So this is the feeling nice, but this is where the negative things start happening because of the stress that's involved, or these areas being involved in stress reactions.
Yeah.
The final area, which is the behavioral area, the prefrontal cortex, that's the key area for controlling our behavior. And it's actually the executive functions in the prefrontal cortex that are vital in what's happening with relapse and deciding and controlling whether relapse and rehabilitation will work. So the work that Marco is doing in the prison and which Pietro is working on for his project with me, that's to do with this area here. So it involves a different area, glutamatergic pathways in the nucleus accumbens and amygdala. It's mainly about how these areas are linked to the prefrontal cortex, which is the executive functions. So the main thing to take away from this is that the areas that are involved in the addiction are effectively moving from the reward centers in one area, which make you feel good, to the second area, which are the stress areas, which make you feel negative. And then finally, the behavioral area, which is the one that allows you to say whether you will have another drink, whether you will have another cigarette, whether you will try to get more drugs, whether you will go shopping again, etc. And that decision process happens from the front of the brain in the prefrontal cortex. And those are the executive functions, which is a psychological response rather than a neurobiological response. Does that make sense?
Yes, yes, yes.
Okay.
Posso fare una domanda?
Chiederei a Pietro di fare una sintesi.
Beh, allora, come ha detto lui, la prima parte che abbiamo visto è quella legata al piacere,
Dopamina.
alle binge intoxication che stavamo dicendo. La seconda invece sì, parte dell'amigdala centrale, ma anche l'altra in verità.
Sì.
È quella che stimola invece la produzione di neuromodulatori, neurotransmettitori che portano all'attivazione di parti del cervello che sono responsabili di una sensazione di ansia, di malessere, per cui ciò che è negativo, e la parte, come l'ha chiamata prima, the dark side of it, la parte oscura, il lato oscuro della dipendenza. La terza è la medial prefrontal cortex, che è parte del lobo frontale, che invece è incaricata del comportamento e delle funzioni esecutive, che è questo termine che si utilizza per appunto spiegare come ci adattiamo a situazioni diverse, e per cui se, per dire, no, sono una persona che beve frequentemente e ho già bevuto 2 bicchieri di vino, le funzioni esecutive sono quelle che sono incaricate di dire ok, bevo un altro bicchiere di vino, oppure no, va bene così, non bevo più, no? E queste sono appunto in collegamento con la ventral tegmental area, e quindi cioè nucleus accumbens, ventral tegmental area e poi corteccia prefrontal cortex.
Quindi
Sì,
questo potrebbe spiegare anche il fatto che maturando attorno ai 18-20 anni la corteccia prefrontale,
esatto.
ci sono dei pericoli maggiori nell'assumere droghe da giovani, perché è più facile diventare tossicodipendenti, da un lato. No?
Esattamente, ed è questo infatti il progetto che abbiamo cercato di sviluppare con Marco all'interno del carcere, perché siamo appunto andati a vedere quando si è sviluppato la dipendenza,
Sì.
ma anche se ci sono stati dei traumi cerebrali durante questi periodi di sensitività, no? In cui il cervello si deve sviluppare.
Esatto. Okay. Mentre, vabbè, no. Ok.
Posso poi io fare una domanda?
Certo.
Scusa, non so se Francesco doveva finire la sua...
Posto era relativa appunto alle funzioni esecutive, all'alterazione delle funzioni esecutive.
Buono, buono. Allora, praticamente da quel che ho capito, la parte precedente, quella che parlava dell'azione inibitoria, in qualche modo ha a che fare con la fase di carenza, quella che i tossici definiscono come carenza.
Sì, la seconda.
Sì, sto male, e quindi anticipano anche talvolta l'ansia e quindi vanno nuovamente alla ricerca per approvvigionarsi, no? Quindi introducono questo elemento di anticipazione dell'ansia, eccetera, eccetera. Questa qui è la parte di Koob. A me interessava molto, dunque, nella penultima osservazione, no? Che nella corteccia prefrontale, per quel che so io, in qualche modo si utilizza la serotonina, è la serotonina che in qualche modo viene utilizzata come trasmettitore per definire questi comportamenti inibitori. E invece qua sembra che, da quel che magari sbaglio a leggere o interpreto male, sembra che qui invece sia implicato il glutammato, che in qualche modo invece ha a che fare con le funzioni eccitatorie. Quindi vorrei chiedere attraverso Pietro ad Ashok in che modo comunica la corteccia prefrontale con il nucleo accumbens.
La corteccia prefrontale con il nucleo accumbens. Ashok, però aspetta, perché questa qui era la cosa che appunto lui non era sicuro di come, perché l'avevi fatta prima questa domanda già.
Ok.
Se era a vino, però non penso che lo sappia.
D'accordo, va bene, allora va bene così, va bene così.
Ma gliel'ho chiesto prima, mi ha risposto prima.
Sì, ma lui vuole sapere i mediatori, i neurotransmitter, se è la serotonina o...
So Ashok,
Yeah.
Marco was asking if so he knows that serotonin is involved in communication between the medial prefrontal cortex and amygdala and nucleus accumbens.
Yeah.
So he was asking how the dopaminergic projection worked, because it's
Unfortunately, I don't know.
Appunto.
I just know that there'll be projection of neurons from one to the other, but in terms of what's happening at the neurochemical level, what I'm telling you guys now is the limit of my knowledge, I'm afraid, because I've never studied it myself.
Va bene, ok, capito, insomma.
Ok.
Pietro,
Grazie.
Dimmi.
se Carlo ti dà fastidio, allontanalo.
Ok, go on.
Yes? Okay, right. So basically what we have is we start with positive reinforcement. And remember the rat in the cage pressing the lever a lot because it was getting its nice stimulation in the brain. That's positive reinforcement there. But then eventually you get to the negative reinforcement. And there's two different things going on here. There's impulse control disorders, which are, we know from OCDs and things like that, that there are these different systems involved, and there's also compulsive disorders where stress is involved. Now, these details aren't important, but the main thing is that with addiction, we start with something that feels positive, but then over time, there is a bit of negative at the beginning, in the way that all of us feel a bit flat or bored after we've been to a great party, or after we've had a really lovely meal. The following day, regular boring life happens, and that's the negative side effect of everything. So there is a negative side effect, but this grows and grows and grows to the point where there's nothing positive left, it's just negative. And that's what the addiction is about. So what Koob and Le Moal did was that they created what's known as this allostatic model of drug addiction. And it's based on what are known as opponent processes. So two processes that are the converse, the opposite of one another, and they involve motivation and emotion. So within this model, something called allostasis is very important. And this is maintaining stability outside our normal homeostatic range. So our normal homeostatic range is the response of the body to everyday events, to make sure that our blood pressure, our temperature, etc., is all normal, and there's a range so that you can fluctuate a bit, but it should stay within this homeostatic range. But allostasis is trying to keep stability when we go outside this range. And what's happening within this system is that it's continually changing across time because of the demands on the body. And the reason for this is that our body is set up to try to deal with extreme conditions. So if we had less food, we're outside our homeostatic range, and so the body will need more and more, and there'll be chronic demands, and the allostasis is to try to maintain some sort of stability as you're going outside this range, and it needs to keep resetting, and I'll demonstrate this in a moment. And so allostasis is defined as the state of chronic deviation of the regulatory systems from the normal state of operation, with the establishment of a new set point, and it's always changing. An allostatic load is the cost the body may have to pay for being forced to adapt to an adverse or dangerous psychological or physical situation. And it basically represents the presence of too much demand on the operation of the regulatory systems. So what we've got are this system which, whenever we go outside our normal range, allostasis tries to maintain some sort of stability outside that. And it's always constantly changing to try to allow us to still be okay outside our normal range. But eventually, there's a cost to pay when we're away from our homeostatic range, and that's called the allostatic load. And this can happen because of dangerous psychological or physical situations. So I'm going to demonstrate that with this theory that they created, which is the opponent process theory of motivation and emotion. So it will become clearer in the next slide. But here we have emotion on this axis here, and we have positive emotion, feeling good up here, and negative emotion going down. And this is as we go through time. And as you will see, what happens is that whenever we do something nice, we have a nice feeling, which is the joy, but our system is set up to bring us back to normal, which is our homeostatic range over here, to bring us back, there's this negative response that our system is set up for to make sure that we don't try to stay up here. And that's what the opponent process theory is about. It's that if we did something that felt nice and there wasn't anything to make us come back to our neutral position, then we would just keep going higher and higher and higher and higher, and that would go crazy. So our system is biologically set up to bring us back down, and so it creates this opponent process, which is that feeling of feeling a bit blue or bored after we've done something exciting. So we have the exciting or pleasurable effect first, and then we have the negative side effect afterwards. And in fact, this theory came about because they were looking at parachutists, because they were trying to understand how is it that people who jump out of planes, which is a dangerous thing to do, are doing this. And unfortunately, I have a video of me throwing myself out of the plane, doing a parachute jump to demonstrate this, but it's in my office, I couldn't play it for you. But what they're saying is that we have someone like myself in that picture or in the video, that when I'm looking out the plane and I'm looking down 13,000 feet, it looks like I could die. So there's fear, there's a negative response here. And that is the first feeling you have when you're doing a parachute jump, this feeling of, oh my God, why am I doing this? And that is there for a little while. But then because of this opponent process that is developed from evolutionary perspectives, there is something that pushes it into the positive. And this is the good feeling afterwards. And in the video, you see me screaming at the beginning because it's bloody scary, throwing yourself out of a plane. But then afterwards, I'm so happy. So initially, this theory was set up to try to explain why people threw themselves out of the plane doing something very dangerous that is scary, so negative emotion, because these people ended up feeling good. With drugs, we have the opposite. We have the nice feeling first, and then we have the negative feeling afterwards. At the general level, do you understand the opponent process explanation?
Yes. È comprensibile.
Yes.
It's very clear.
And so what Le Moal, Koob and Le Moal did is that they used this theory to explain how addiction happens. Because this happens for anything. When you have a nice glass of wine, when you have a nice meal, you have the nice feeling, and then afterwards there's a bit of, yeah, whatever. And then you go back to normal. And when you do something that's scary, you have the negative emotion, but then you have the feeling of, wow, that was exciting, and so you feel good. So this is a system that is part of our neurochemistry already. So they use this to explain addiction. So they say in this, an addictive event causes a large A reaction, so great feelings of joy when you're doing something exciting, with possibly a mild depression as an after effect. So into a great party and you think, oh my God, life is so amazing. And then the following day, you still got to go to work. And you have, in English, we say you feel a bit blue. What would you say in Italian, Pietro?
Un po'...
Luna di miele.
Beh, honeymoon sì, feeling blue.
Quando ti
Feeling
senti
blue,
triste,
diciamo,
un po' giù, no?
giù, sì, giù di morale, giù, sì.
So that feeling of feeling a bit blue is the mild depression of, yeah, I'm feeling a bit bored now, etc. And this period is called the honeymoon period in addiction, because you have more of the good feeling, the joy, excitement, and only a bit of the negative one. And that's why it's the honeymoon period, because after you come back from a honeymoon, you're a bit bored because it was so exciting, apparently. So that's the first phase. But then after repeated experiences, what happens is that the joy is greatly reduced. And this is because of a neurochemical reaction in your body, which results in tolerance. And that is as the body adjusts to the drug. And the But unfortunately, the B reaction becomes stronger. In this case, that means that the negative after effects of taking the drug, such as bad mood swings or craving, become stronger. So I'm going to go back here. So the suggestion is, and you'll see it in a later slide, that you have this after taking your cocaine or whatever, and then afterwards you have the negative feeling. But you have this nice feeling. So you think, okay, I'm going to have some more, and some more, and some more, and some more. So you keep doing this, but what happens is that neurochemically, although this system is there for homeostasis, chemically it's not set up for addiction. So what happens is that the gray area here, the joy, becomes smaller. It's just like this. There's hardly any good feeling from taking the drug, but this becomes bigger and bigger and bigger and bigger. So does that make sense?
Yes.
So initially you have this nice, more good than bad, but then because of the response of the body and your neurochemistry, you develop tolerance. And so the negative reaction becomes stronger. And that's when you start having the bad moods of wanting some more, etc., etc. And then eventually, the addictive stimulus is badly needed. And it's not because there's anything pleasant. All that you're trying to do is to get rid of the negative feeling of this negative B feeling. So you're not doing it for pleasure anymore. You're doing it simply to try to get away from the negative feeling. That's when addiction has set in. So this is the under normal circumstances, the ooh, that's really nice, and then the negative honeymoon period afterwards where you feel a bit bad and so whatever. But over time, if this is our homeostatic point here, you have the first time you take it, you're like, the second time you take the drug, you've got a smaller positive response here than this one, but you see the negative response is bigger than here. Then it's taking you a lot longer to get up to this point here. And you take it, the drug, there's hardly any nice feeling, but the negative response is even stronger. And then as your body is trying to get back, it never, even with the fourth time, you're not doing taking the drug because of any positive feeling. You're just trying to move upwards from here so that you're feeling less shit. And each time it's getting worse and worse and worse. So each time this is happening, the drug is simply to try to take you away from this horrible feeling here. And this is the allostatic state, which is each time it's changing from this one to this one to another to a low one. Because remember that the allostatic points, those are changing constantly because you're in a different deprived state. So just to summarize again, this is under normal circumstances, the nice feeling followed by the negative feeling. And so you have the honeymoon period where you think, oh, but it was really good. It was worth this horrible feeling to have this nice feeling. But then when the next time you do it, the feeling is not so good, the good feeling, but the negative feeling increases. Then you take it again and you're barely getting any positive feeling, but the negative feeling is increasing. And then at this point, this is when addiction has set in, because you're not taking the drug for the positive feeling, you're taking it simply to reduce the negative feeling. Okay?
Okay.
Right. So there are three important phases: the initial positive reinforcing effects of the drugs in the reward areas. Then there's the chronic use, which leads to the downregulation of the dopaminergic system and underactivation of the reward pathways. So this is what's happening within the same system, that within those neurons, they're kind of going to sleep. The dopamine isn't really having much effect. So that's the within system adaptation. And then the third phase is the recruitment of those opponent processes, so the negative effects, which are around this, the stress system with that CRF in the hypothalamus. And so this is where you've got different brain areas, hence the between system adaptation, between one area and another area. We've got three phases: the nice good feelings, then the good feelings not really being there, but more of the negative feelings, and then eventually you're in that stress situation where the only thing you're thinking about is having the drug to reduce the negative feelings. So the initial positive reinforcing effects of drugs in the different brain areas, they increase the extracellular dopamine, which is what we saw with the effect of the morphine, sorry, the heroin, which is converted to morphine, and the cocaine in the synaptic cleft. And this is correlated with subjective feelings of high and euphoria. So if you have more dopamine in those areas, you have this feeling of, oh, this is cool, I feel great, etc. And as I said before, it's related to the speed of entry of the drugs into the brain. So the faster the brain can take up the drug, the quicker it's associated with the reinforcing effect. So don't worry about this phasic versus chronic firing. So this is an example of, I don't understand people who drink shots, you know, the shots of vodka, etc. I prefer to have a nice bottle of glass of wine that I drink calmly as I'm having a conversation and talking to someone, or a nice beer. But there are some people who want to have the really quick shot. Now, this is because the shot, because it's so concentrated, gets quickly into the blood system, and therefore they get the happy feeling more quickly. So can you see how even with alcohol, it's the same thing? If it's something that goes quickly into the blood system and you get the nice feeling quickly, then people will want more of it. And this is why after the first shot, people don't stop. They want a second and a third and a fourth shot, okay? And it's also related to the pharmacokinetic properties of the drugs. So the difference between cocaine and methamphetamine, etc. Because all of the different drugs have got different biochemistries. They act on different parts of the brain. And then there'll also be different things to do with their reuptake and how quickly they're cleaned out of the synaptic cleft. And as I said right at the beginning, they're not working on different brain areas. They're mimicking the response of those natural reinforcers of food, drink, sex, alcohol, etc. Or actually food, drink, food, sex. So they're natural reinforcers. They're not working on a special new system. So just in the same way that you can give morphine to someone who's in pain in a hospital, the cocaine, the heroin is exactly the same thing. It's just that it's coming in a different format, but it's these natural reinforcers that we already have set up in the brain. Then phase 2 is the downregulation of the dopaminergic system and the hypoactivation in the brain reward areas. So this is basically where the neurotransmission from one neuron to the other is reduced because of what's happening in that cleft area. And then the whole reward area becomes lower in activity. So importantly, drug-related cues can also increase dopamine release into these areas. So the reason that this is important is that it's not necessarily just having the drug itself. As you will see with some research I'm going to demonstrate to you, it's any cue that makes you think of the drug can also make you actually release some of these drugs into the synaptic cleft. So it's not just the drug itself. Eventually, just thinking about the drug can do it. So Volko, Nora Volko, who works at the, I think, NIH in the States, she used PET scanning to examine dopaminergic release in cocaine-addicted individuals and correlated this. So this is a biological marker, so looking at the PET scans, with the self-report of craving and addiction severity. So she had in people who were cocaine addicts, and this is defined as more than 4 grams of cocaine per week. And what she did is that she presented them a cocaine-related video of someone snorting cocaine here. And she compared that to them looking at a video of a nice stream in the mountains. And so they did this, showing them the cocaine-related video or this. So they're not getting the cocaine in this study. They're just seeing the video of someone snorting cocaine or a video of a mountain stream. And what they found is that just watching the video, this video here, significantly increased dopamine release in the striatum. So this is the response to this video here, and this is the response to that video there. Now, unless you're a neuroscientist who really cares about the brain scans, just accept from me that there's increased dopamine in this brain here. Mm-hmm. What they found is that the more the dopamine that was released in these cases, the bigger the correlation that the individual self-reported of when they saw this. So they actually asked them how much, while they're watching these videos and afterwards, how much do you want to have your cocaine? Because they knew these people are addicted. So they asked them, how much do you want to have cocaine now? And what they found is that the more dopamine that was released here, the more these people reported, I really want some cocaine. So what this study demonstrates is 2 things: that neurobiologically, there is a difference here between seeing a cocaine related, actually it demonstrates a couple of different things. The first thing is that the release of the dopamine does not have to be only from taking the cocaine. It can happen from just seeing someone taking cocaine. So that is why it's addicts find it really difficult being around other people taking the drug if they're trying to reduce their drug intake, because the cue of seeing someone smoking or having alcohol, etc., is enough to release the dopamine, etc., in their brains. So that's the first thing. The second thing is that we can see biologically here that compared to just seeing a regular scene, there is more activity. And then the third thing is that when you ask these individuals, how much do you want to have your cocaine or your alcohol, etc., afterwards, their rating on a scale of, say, 1 to 10 is much higher after they've seen this than this, and it correlates with the amount of dopamine that's being released here. So does that make sense?
Yes.
Yes, yes. Yeah.
Okay, so then the downregulation of dopaminergic and hyperactivity. So this is again in phase 2. This is in the caudate nucleus and the putamen. This is for the neutral video, and what you see is that there is a different activity. In this case, there's less dopamine, so it's the downregulation of the dopaminergic pathways in the neutral compared to the cocaine cues. And there's the change in craving. So how much do you want the cocaine is linked to, this is the change in the amount of activity they saw in the dopaminergic areas. So this is saying the same story, that there's a difference in what's happening in those areas that release dopamine when you see the cocaine-related cues and the neutral cues. And here we're saying there's a positive relationship between the change in the dopaminergic areas and the amount that the people want to have their cocaine. And then the changes in the dopaminergic and reward mediated pathways in significant reductions in receptor availability. So basically, you don't have that many receptors available in the second neuron to take up the dopamine. So effectively, that's why you need to have more and more, because basically the second neuron just have the capacity to take any more dopamine because it's reduced its receptors. So this results, this is there for months after protracted abstinence. So it's not a case of just stopping the cocaine or the alcohol for a couple of days or a couple of weeks. It's there for many months. So it takes quite a while for these receptors to bounce back to the normal level that they had before the addiction. And this is evidenced by reduced release of dopamine in response to psychostimulants. So even when you try to stimulate the dopamine release in these drug abusers, you get lower dopamine release. So even when you're trying to make the system fire more dopamine, you don't get that much dopamine. There's also reduced salience and incentives for natural reinforcers. So natural reinforcers would be the food, sleep, etc., the things that we usually get pleasure out of. There's a reduced need for or what desire for those. And this is because there's such a big increase in the thresholds for reward that you would need a lot of any of those to actually feel anything positive. Was someone asking a question just now?
No, sorry, I was just pointing out that the reduced rate of the DA releases, so there's physically less receptors.
Yeah.
And so even if you try and stimulate more, they're just... Non so se avete capito, in pratica c'è una risposta negativa nella release, no, anche se si cerca di stimolare la come si dice, uptake, sì, della dopamina, c'è una risposta negativa perché fisicamente non ci sono abbastanza recettori per far attivare la risposta, no? E quindi niente, c'è l'increase l'aumento nella threshold, nella soglia
della
di
dopamina nello spazio sinattico, sì. tra le cellule.
Okay. Forward.
Yep. Okay. So then there's an increase in drug taking to compensate for that increased reward threshold. And so we don't want the good things of life, the food and things like that are our natural reinforcers, because we would need far too much of those to meet the demands of this increased threshold. But we do seek more drugs to compensate for this. So whereas before it was a small amount of cocaine, now you need 2 hits of cocaine or 3 hits of cocaine. And what's happening is that there's a shift from feeling high, which is the initial thing, to using drugs just to feel normal. So it's no longer about taking this for a pleasure. It's for just trying to come back to some sort of homeostasis. And there's reduced activity in the dopaminergic circuits, which leads to decreased activity in the orbitofrontal cortex and the dorsolateral prefrontal cortex. So this is where the link to the frontal lobes becomes important. So this leads to the poor control of behavior and craving and compulsive behavior. So what we've got is the changes in different areas of the brain are resulting in less pleasure, more drug taking, and a lower control of behavior because of that link to the prefrontal cortex. Here in this one here, we've got dopaminergic release for a healthy control, a cocaine abuser 1 month, I think, after trying to recover, and this is 4 months after. And what you see is that there's a big difference between healthy control and someone who's given up the drugs 1 month ago. Here, there are some changes beginning to happen. You're seeing more red here, which means more activity in those central areas of the brain compared to here. But it shows that even 4 months after stopping the drugs, you still haven't bounced back to the dopaminergic system that was before. Okay?
Mm-hmm.
And here we've got a control and an cocaine abuser, and this is about receptor occupancy. And here you've got a control versus a meth user. So this is just about drugs. And is that abusers on this side, they've got much lower receptor density, which means they're not going to be able to fire that much. And here we've got receptor density again on this side, and on this side, metabolism in the orbitofrontal cortex, but that's quite technical, so we won't go into that. So then finally, we move to phase 3, which is the recruitment of the opponent processes. And this is the side of chronic drug use. This is where you've got release of that CRF in the amygdala during withdrawal. And this results in the anxiety responses, and this subsequent drug intake is blocked by antagonists. I'm not going to talk about that because it's too technical. There's evidence for a role of norepinephrine, particularly in alcohol withdrawal. So some neurotransmitters are more involved in some chemicals, such as alcohol, than others. And there's increases in that thing called dynorphin in the amygdala and the nucleus accumbens, and this is also associated with the negative emotional states. So, and then finally, there's chronic decreases in the anti-stress system, such as the neuropeptide Y. So what we have is activation of this anti-reward system, and this is what makes recovery difficult because it's compromised. And this is where you can get relapse. So we've got the anti-reward systems are compromised during recovery, and because of that, the chances of relapse because of stress are increased. Because in this condition, the system is really quite damaged, and so it's very easy for it to want to get more drugs to come back to its original levels. So it can increase the chances of relapse by maintenance of negative emotional state. It heightens the sensitivity to acute and chronic stresses in the environment. So whereas you might be slightly irritable and just think, oh, tomorrow I'll feel okay, or feeling slightly bad, something at work, where you think, oh, it's not a big deal. In this phase for an addict, these small things, they become quite big, and so the result is that the possibility of relapse is greatly increased. You and I, we would think if we're feeling a bit stressed about something, we'd think, okay, by this evening I'll be okay, but they can't deal with that. They need to have the drug again. And there are neuroadaptational changes which can be relatively long-lasting. And we saw with that brain scan of the cocaine abuser after 4 months that it still hadn't recovered the dopamine activity, it still hadn't recovered to normal levels. So the relapse, the chance of this relapse can occur even after a long time. And from what I know of people who work in addiction, the likelihood of someone relapsing is really, really quite high. So finally, these are the different neurotransmitters implicated in the different motivational effects of withdrawal. So some of them are to do with stress, like this neuropeptide Y, or corticotrophin releasing factor, the CRF. GABA is involved in anxiety and panic attacks. Decreased dopamine results in dysphoria, so the opposite of euphoria and feeling a bit flat and etc. Decreased serotonin results in more pain, dysphoria, depression, etc. So we see that there's quite a few different neurotransmitters that are involved in our emotional feelings, which then have an impact on our behavior towards other people, towards drugs, etc. And each of them has a different impact. They also have different impacts on different brain systems. And what we see overall is that there is quite a lot of variability in which areas of the brain they affect and what the rate of recovery is. So to kind of summarize, because this is the last slide, to summarize, the initial work by Olds and Milner was really important for showing us basically which center in the brain is involved in reward. And from the work on the rats, they were able to see that this area in older parts of the brain, in the ventral tegmental area and the nucleus accumbens, are really quite important for any good feelings that we get. And we know that these areas are activated naturally anyway by drinking, food, sex, etc. And what's happening with addiction is that external chemicals, which we now refer to as drugs, but they're all neurostimulants, they all work on exactly that same area. But what's happening is that they're affecting the activity by either making the dopamine more available, which results in the really nice feeling, or making the dopamine less available, which is the negative feelings. And the psychological models of behavior are around component process theory, which says that although initially our system is set up to allow for us to reach homeostasis by having an opponent process to bring us back down to earth. So if you have a great feeling over a party or whatever, afterwards you'll have a bit of a negative feeling, but that will be the honeymoon period. And usually we just think, oh yes, it's always like that. After a great time, you have a bit of feeling blue. But what happens with drugs or with addiction is that over time, the positive feeling reduces, but the negative feeling increases, so that eventually the person is not taking drugs simply for any positive effects. They're only taking the drugs to take away the horrible negative feelings. And that's when addiction is set in and they're on the dark side. And at that point, the front of the brain and its ability to control behavior is what's been impacted. And so the ability to say, no, I won't have that drug, or I won't go to the party, or I won't drink, etc., is what's been severely compromised. And so a lovely example is the work that Pietro did with Marco in the prison, where we saw that with the people who are part of the drug rehabilitation program, compared to healthy people who are not drug addicts, they perform more poorly on a task that I've developed of how the front of the brain manages behavior, because that behavioral element in the front of the brain is the one that is ultimately responsible for making the decision whether you're going to have another drink or another drug, etc., etc. And what we see behaviorally, certainly from my assessment that Pietro used, that their behavior is severely compromised. And because these systems take a long time to recover, the neuroreceptors, the functioning of these systems, the way that different areas of the brain communicate with one another, because of these between systems adaptations, you have the fact that even if someone has stopped taking the drugs, their system is so severely affected that it's going to take many months for it to recover. And that's what people in drug rehabilitation are trying to do, is to work out how can we help these people to recover, so that just seeing someone else taking the drugs or smoking, etc., doesn't give them a relapse. And from the little I know about drug rehabilitation, it's not working, but that's just speculation. Thank you very much.
Thank you.
Very much.
Thank you.